üçgen. So today our speaker is Enis from University of Groningen. And he will tell us about explicit Vologodsky integration for hyperelliptic curves. Yeah, Enis.
Okay, thank you, Turku, for the introduction. And thank you also for the invitation. It's very nice to be a part of this beautiful program. Okay, I think it's recording. Yeah, okay. So
yes, it's recording. Thanks. Sorry.
Okay. Yeah. Okay. This talk is based on my two papers, and the first of which is a joint work with Eric Katz from the Ohio State University. So in the introduction, I will mention some terms, then I will explain them in detail later. So for us, P will be a fixed prime number, and Coleman integration is a method for defining p-adic integrals on varieties with good reduction at P. So here, p-adic integrals means, line integrals on spaces which are defined over p-adic fields. So if you don't know much about p-adic fields, don't worry, I'm going to define them. But basically, they are just p-adic versions of the field of real numbers or the field of complex numbers. So this is what Coleman integration is. On the other hand, Vologodsky integration also produces such integrals on varieties. And the advantage of this is that it does not require that we have good reduction at P. And we know that these two integration theories are the same in the case of good reduction. So we can say that Vologodsky integration is a generalization of Coleman integration. And yeah, so these integrations have numerous applications in arithmetic geometry, and I want to list some of those. So first of all, they are used to find torsion and rational points on curves. So let me be more precise here. Let X be a curve, a smooth curve over the field of rational numbers of genus at least 2. Then thanks to Falting's famous theorem, we know that there can be only finite many rational points on this curve. However, his proof is ineffective in the sense that it does not give a method or algorithm to compute these rational points. And I think, in arithmetic geometry or in number theory, we basically trying to find rational points on this kind of curves. We know that there cannot be a general method, but for some curves under some conditions, there are some methods we can apply, and some of these methods use these integration theories. And the second is relevant to the first one. So these integration theories are used to find uniform bounds on curves. So this is a very famous conjecture in Diophantine geometry. It says the following: let G is an integer at least 2. And the conjecture says that there must be a constant B depending on G, such that every smooth curve X defined over Q of genus G has at most B rational points. Again, thanks to Faltings, we know that rational points, the set of rational points is finite, but this conjecture says that there is an upper bound for all these kind of curves. There is an uniform bound. And there are a few results regarding this conjecture, and some of them use these integration theories. So the third one is about computing p-adic heights on curves. So p-adic heights are just p-adic analogs of height functions that are used in arithmetic geometry a lot. Some people call them, Néron-Tate height, or canonical height, or naive height, whatever you call them. These are just p-adic versions. And some of these p-adic heights can be computed using these p-adic integrations. And another related theory is the computation of p-adic regulators in K-theory. As long as you can compute p-adic heights, you can also compute some p-adic regulators. And this is very general. I mean, you can compute some p-adic regulators in higher K-theory. Okay, these are the applications. And it turns out that some of these applications rely heavily on explicitly computing these integrals. And Coleman's construction, recall that that was a construction for varieties that have good reduction at P. This construction is quite suitable for machine computation. So basically, there is one important object, what we call a lift of Frobenius map. As long as you can compute the action of this map on differential forms, you know how to compute Coleman integrals. And there are practical algorithms due to Balakrishnan, Besser, Brotchov, Kedlaya, Müller, and Teichmann. I mean, I'm mentioning these names here like this. It's because, there are several papers. For example, the first one is due to Balakrishnan, Brotchov, and Kedlaya. For example, they only deal with odd models of hyperelliptic curves, and they only consider some specific differential forms. So it's extended in other papers, etc. But on the other hand, when it comes to Vologodsky integral, his original construction is quite hard. And because of this, Vologodsky integration has been so far difficult to compute. Nevertheless, in joint work with Eric Katz from the Ohio State University, we gave an algorithm for computing Vologodsky integrals of holomorphic one-fourths on bed reduction hyperelliptic curves. And the idea was not to use Vologodsky's construction directly. The idea was to reduce to known cases. And we will see what I mean by that. And to the best of my knowledge, this is the first attempt in the literature to compute these integrals in the case of bed reduction. So it is quite interesting. But it has the drawback that this algorithm deals only with holomorphic one-forms, regular one-forms. But for some applications like p-adic heights on curves, it is necessary to deal with more general meromorphic one-forms. So to that end, in a different paper, I extended this algorithm in a natural way to also cover meromorphic forms. And my goal in this talk is to explain the algorithm. So let me summarize the algorithm. So we have an hyperelliptic curve x given as the projectivization of y squared is equal to f of x, this kind of equation. Here, f is a polynomial in x, it's a separable polynomial. So in the first step, we construct a covering of our curve that has originally bed reduction in such a way that every element in the covering can be embedded into another curve, which is either a rational curve isomorphic to P1 or a hyperelliptic curve of good reduction. So this part is a bit weird because, we have a curve that has bed reduction, but I'm just saying that we can find a covering so that each piece has a good shape. And basically constructing such a covering is more or less equivalent to finding a semi-stable model. I'll come to this later. Okay, in the second step, based on a comparison theorem, we will relate Vologodsky integrals on the big curve as linear combinations of Vologodsky integrals on the curves xi's. And we will see that these linear combinations are explicit. So if we want to compute Vologodsky integrals on the big curve, it will be enough to compute Vologodsky integrals on these smaller curves. And in order to compute Vologodsky integrals on xi, since there are two types of these curves, we will parameterize xi if it is rational. In this case, the forms will be represented by a parameter, so integration will be easy. Otherwise, since in the good reduction case, Coleman integrals and Vologodsky integrals are the same, we will just make use of the known Coleman integration algorithms if xi is a hyperelliptic curve of good reduction. So this is the idea, and in this talk, I'll try to explain these steps in detail. So, okay, this is the overview. In the first section, I'm going to define p-adic numbers. In section 2, I'm going to talk about Vologodsky integration. In section 3, I'm going to explain Berkovich-Coleman integration. So far, I didn't say anything about this integration, but basically, it's a bunch of Coleman integrals, at least for curves. And this will be a middle step for us in the sense that first, we will express Vologodsky integrals on the big curve in terms of Berkovich-Coleman integrals. Then we will express these Berkovich-Coleman integrals in terms of ordinary Coleman integrals. And in section 3, there are two parts. First, I'm going to say something about Berkovich spaces. These are certain non-Archimedean topological spaces. These spaces are important for us because Berkovich-Coleman integration is defined on such spaces. And in the second part, I'm going to say something about integration. In sections 2 and 3, I'll be more general. But in section 4, we will only consider curves. And in section 4, I will try to compare these two integration theories for curves. And we will see that the difference will be given by a combinatorial object, what we call tropical integration. I mean, this name sounds so cool, but it's a very cheap, easy object in practice. And finally, we will conclude with a numerical example computed in SageMath. Okay, p-adic numbers. So for us, p will be a fixed prime number. And we have a non-zero rational number a. And the p-adic valuation of a is defined as follows. First, we consider the case where a is an integer. So in this case, the valuation will be the maximum power of p that divides a. If a is not an integer, we can write it as the ratio of two integers. Both are non-zero, r and s. But since r and s are integers, we know how to define their p-adic valuations. And valuation of a is just defined as the difference right here. Okay, this is the p-adic valuation, and we will define p-adic absolute value. So here we have a rational number a. The corresponding absolute value is defined as 0 if the number I started with is 0. Otherwise, it is just p to the minus valuation of that number. So basically, I mean, in this p-adic valuation and p-adic absolute value, we only care about the number around p. We just ignore all the other powers. For example, it can be a very big number, you know, in the usual sense. But for example, it doesn't. For example, p does not divide this number, and the valuation will be 0. So let me give you this example. Here we have an integer n, and what is the valuation of p to the n? So this is exactly n, because p to the n divides p to the n, but p to the n plus 1 does not divide p to the n. So this is n. And the p-adic absolute value of p to the n will be, just by definition, p to the minus n. So p-adically, we can say that p to the n is very small. It is close to 0 if n is large. So this just says that p to the n is close to 0 p-adically when it is divisible by high power of p. Okay, so we have a space Q on which we defined an absolute value. These are the properties. The p-adic absolute value of A is 0. Sorry, there is a typo here. It's 0 if and only if A is 0. And it is multiplicative. In the usual absolute value, as you know, we know that the absolute value of A plus B is less than or equal to absolute value of A plus absolute value of P. And here we say something stronger. We are saying that the p-adic value of the sum is less than or equal to maximum of these two. So this is indeed an absolute value over Q. So there is a fact, Q is not complete with respect to the metric coming from this norm. Okay, we can complete it, and the completion is denoted by QP, and it is called the field of p-adic numbers. But this is exactly how we construct the field of real numbers from Q, right? I mean, instead we use usual absolute value. So in that regard, we can say that QP is just a p-adic analog of the field of real numbers, p-adic cousin of R. So from R to C, okay, how do we do this? I mean, R is not algebraically closed. We consider the algebraic closure C, and this algebraic closure is also complete. So we can play the same game for this field. It turns out that QP is not algebraically closed. Okay, we can consider the an algebraic closure. And it turns out that this algebraic closure is not complete. Okay, we can complete it. The completion, denoted by CP, is algebraically closed. And this CP is just p-adic analog of the field of complex numbers. And CP is complete and algebraically closed, like C. Okay, so both QP and CP, these are complete spaces. So we can try to do analysis over spaces defined over these fields. Well, it turns out that many concepts and results from classical analysis carry over easily, but integration does not. Okay, why is that? Well, I mean, one sentence reason is that the p-adic topology coming from p-adic metric is totally disconnected. Let me be more precise here. As in the classical case, an approach will be to integrate differentials locally and do analytic continuation and get a big integral on the complete space. So in the p-adic world, we can integrate differentials locally exactly in the same way. There is nothing wrong with that. But because of totally disconnected topology, whenever we have two open balls, there are two possibilities. Either they are completely disjoint, or one of them is contained in the other. So this makes naive analytic continuation impossible. So let me show you a picture. On the left here, we have two open balls, and as you see, they don't intersect. This is fine for us. And here, one of them lies in the other. This is fine for us. But the picture on the right, this is not good. This is not possible in the p-adic world. As you see, there's a non-trivial intersection here. So in the p-adic world, there are no non-trivial intersections. Hence, analytic continuation is not possible in the naive sense. And Coleman integration, Vologodsky integration, Berkovich-Coleman integration, basically, they use some other methods to define a global integration on the complete space. Okay, what is Vologodsky integration? So here we have X. This is a smooth, geometrically connected algebraic variety over a finite extension of QP, what we denoted by K. And we consider a closed one form. It's a differential form, omega. And we have two K rational points, X and Y. So to this data, Vologodsky associated an integral denoted by this symbol. And this integral satisfied the expected properties. I'm not going to list them one by one, but basically, for example, it is additive in endpoints, it is additive in this form, and it is functorial, etc. And we call this integral the Vologodsky integral. The important part for us is that when X has good reduction, as we discussed in the introduction, Vologodsky integral is the same as Coleman integral. So, I mean, this is just a generalization. Okay, this is one integral. What is the other? Here, we have an algebraic variety, X over Cp, and it is possible to consider a corresponding Berkovich space. But we do, I mean, it's denoted by X to the n, the Berkovich analytification. Unfortunately, I don't have time to explain this Berkovich spaces, but we will see some examples and some pictures. So this is basically a nice topological space. It's a non-Archimedean space. And here I wanna list some properties of this construction, because on the left-hand side we have an algebraic object, and on the right-hand side we have an analytic object. I mean, the algebraic object is proper as an algebraic variety if and only if the corresponding Berkovich space is compact and Hausdorff. I mean, this is great because, I mean, recall that what was the big problem in the p-adic topology? It was totally disconnected. And here I am talking about an Hausdorff space. So this is indeed unbelievable. Second part, the algebraic variety is connected if and only if the Berkovich analytification is path connected. This will be very important for us. We will use them. And generally, all connected components of a Berkovich space are actually path connected. So this is another nice thing about Berkovich spaces. And finally, the Berkovich space contains all CP points on our curve X. Actually, this is much, much bigger. So from now on, let K be a finite extension of QP. And this is, again, a complete. And we fix a smooth, proper, and geometrically connected curve X over K. So again, it's a basic fact in algebraic geometry. We can find a semi-stable model of this curve, which is possibly defined over a finite extension of K. And here, by extending K if necessary, for simplicity, I just assume that my semi-stable model is defined over K. Actually, it is OK model. OK is just ring of integers. I mean, some integrality here. And there are two important objects that we can attach to this covering. One is gamma. This is the skeleton. I'm going to explain what it is. And the other is a certain map, tau, from the Berkovich space to the skeleton. So what are these? So gamma is a certain closed subset in my Berkovich space, which is homeomorphic to the dual graph of the special fiber of my model. And tau is a kind of dual of the reduction map. So this reduction map is not very, very important in algebraic geometry, but it's very important in rigid geometry or Berkovich geometry. So, I mean, I didn't define this properly, so let me give you an example. So here we consider the hyperelliptic curve given by this equation. As you see on the right-hand side, we have a polynomial of degree 6. And one can easily check that 5 is a prime of base reduction for this curve. And actually, the corresponding reduction is a genus 2 banana curve. What is it? It is the union of two projective lines intersecting at 3 points, as in this picture. So this is my special fiber. Okay, what is the dual graph? I mean, we have two components. It means that there will be two vertices, and these two components intersect in 3 points. It means that there will be 3 edges. So this is our dual graph. So from this, we will see the corresponding Berkovich space, which is this picture. This picture is due to Joseph Robinov, represents the Berkovich space. I mean, I cannot say that this is completely fine, but it is, I mean, it's not possible to draw these curves anyway. So it represents our curve. So first of all, this is the complete curve. And here we have two vertices, two vertices. And here we have 3 thick lines, one here, one here, one here. And this is the skeleton. And notice that this is exactly the dual graph. So recall that gamma is a closed subset of our curve, which is homeomorphic to the dual graph of the special fiber. So how do we get this picture? I mean, it's all about understanding the reduction map, because on the left-hand side, we have Berkovich space. On the right-hand side, we have special fiber. So let's take one point from the special fiber. If it is a smooth point, then it is inverse image on the reduction map will be a Berkovich open disk. And what you see here, this small tree, is actually a Berkovich open disk. And similarly, this one, and this one. Since there are infinite many smooth points in this picture, in this special fiber, there will be infinite many open disks directed away from these vertices. So on the right-hand side, we have a semi-stable model. The other possibility is that we can have a knot, a ordinary double point. So in this case, the inverse image of such point will be a Berkovich annulus. And notice that we have 3 nodal points. It means that there will be 3 Berkovich annuli, and one of them is here, this thick line with these trees around it, and similarly one here, one here. So this is how we construct the Berkovich space from the reduction map and the special fiber. So what is tau? So tau is basically a map from this Berkovich curve to the skeleton. And I mean, there is a formal way of defining this map, of course, but let me just say that if we have a point right here, its image under tau will be the closest point on the skeleton, just right here. If by luck, you are just, if you pick a point right here, the image will be just identity. So this is exactly what tau is. And as you see, the skeleton is this space. I mean, I love this name. I mean, skeleton is indeed skeleton. Okay, so what is Berkovich-Coleman integral? Here we have a smooth CP analytic space. It will be a Berkovich analytic. We have a closed analytic one form, omega, and we have a path. And to this data, Berkovich associated an integral denoted by this symbol. And this integral again satisfies the expected properties. And as you see, and we have a notation here, gamma. So it is path dependent in general. So in the sense that it does not depend on the endpoints all the time. Generally, it's path dependent. And we call this integral Berkovich-Coleman integral. I didn't invent this name. I just follow some other people. And if the path is a closed path, if it's a loop, I will call the corresponding Berkovich-Coleman integral a Berkovich-Coleman period. So what are the properties of this? So again, if X has a good reduction, Berkovich-Coleman integral is the same as Coleman integral. So in other words, Berkovich-Coleman integral is another generalization of Coleman integral. And another important thing is that this is very, very important for us, and it is not true for Vologodsky integration. The Berkovich-Coleman integral is local. Okay, what do I mean by that? If we have a space U, and if our path lies in U, then the Berkovich-Coleman integral on X can be computed from U, smaller space, the restriction of our differential forms to U, and gamma. I mean, what is the advantage of this? Maybe X is very complicated space, but U is comparatively simple. When this is the case, it is easy to compute. Okay, so we will compare these two integration theories. Here again, we have a finite extension K of QP, and we fixed a smooth, proper, geometrically connected algebraic curve, X over K. So this is an algebraic curve, and on this space, we have the Vologodsky integral. But we can consider the corresponding Berkovich space and the corresponding Berkovich-Coleman integral. First of all, Berkovich-Coleman integral is generally path dependent. Just from this observation, we can say that these two are not the same in general. Hence, we have a natural question: what is the difference? So the relation between these two integrals will be provided by a combinatorial object, what we call tropical integration. And again, this is very cheap object, and it is quite easy to compute in practice. So let me define this. Here we have a finite and connected graph, gamma. And as you guess, this will be the dual graph of a special fiber of a semi-stable model. We have V of gamma, E of gamma. These are the set of vertices and oriented edges. Here we have an abelian group A, and a tropical one form on gamma with values in A is a function from the set of oriented edges to A, such that eta of minus A will be the minus eta of A, and minus A will be just one edge, the same edge with the reverse orientation. Recall that we consider edges as oriented edges. And the second condition says that whenever we have a vertex, we consider a sum, the sum of eta is, where this sum is taken over all edges that are adjacent to V and directed away from V. And this sum will be zero. When these two conditions hold, we will have a tropical one form, and we will denote the set of such functions by this symbol. So let me say that this tropical one form is just a harmonic one cochain. This is just another name for the same object. Because I mean, this first condition is just being a cochain, and the second is just a harmonicity condition. Okay, example. Here we have an oriented edge, E, from the vertex V to the vertex W. And I define a function, eta E, which takes the value plus or minus 1 if the edge I started with is plus or minus E, otherwise it is 0. And this H1 of gamma is denote the set of 1 cycles. Okay, we have a graph, right? And there might be some cycles. For example, this set will be empty if gamma is a 3. And if we have a cycle C in our graph gamma, then the function defined like this, eta C. I mean, here we consider these the same constants, but for E, we get this eta E defined right here. And this will be a tropical one form. I mean, the first condition is clear, and the second condition comes from the fact that C is a cycle. So cycle condition on the left-hand side, will give you the harmonicity condition on the right-hand side. Okay, now I'm ready to define tropical integral. Here we have eta, this is a tropical one form, and gamma is a path which is given as a sequence of edges, E1, E2, dot, 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 EL. And the tropical integral of eta along gamma is just the sum of these values. That's it. And eta takes values in A, and A is an abelian group. This implies that the tropical integral is just an element in A. Okay, finally, we are ready. Okay, recall that in the beginning, we fixed a curve over K. And again, we just assume that we have a semi-stable model over the base field. And recall that we have the corresponding objects, the skeleton, and the retraction map, gamma and tau. And recall that gamma is a certain closed subspace, which is homeomorphic to the dual graph of the special fiber. From now on, I identify gamma with the dual graph so that I see gamma as a graph. And I state the following proposition. Okay, this is a cycle space with coefficients in CP. And here we have a tropical one forms with coefficients in CP. These are both CP vector spaces, and it turns out that they have the same dimensions over CP. And moreover, there exists a basis C1 dot 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 CH and eta 1 dot 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 eta H, so that the tropical integral of eta J along CI is just a tropical, and it's just a Kronecker delta. So it's a kind of a dual base. Yeah, so we have these cycles, and I am using an important property of Berkovich spaces. So whenever we have a path, it is on the dual graph, it is possible to lift it to the Berkovich space. And here, for each Ci, we lift it to a gamma I, so that this condition holds. Since Ci is a loop, since Ci is a cycle, the corresponding path will be a loop. So finally, I am ready to state my theorem. And here we have a meromorphic one form on our curve that we fixed in the beginning. We have two rational points, and we pick a path gamma in the Berkovich space from X to Y. Okay, how do we know that such a path exists? Recall that the algebraic curve is connected if and only if the Berkovich space is path connected. But this is how we pick X in the beginning. So such a path indeed exists. So the theorem says that we have the following equality. On the left-hand side, we have the Vologodsky integral. On the right-hand side, we have the Berkovich-Coleman integral minus an expression, what I call a correction term. What is the advantage of this formula? I mean, on the left-hand side, there is something we want to compute. And on the right-hand side, there are Berkovich-Coleman integrals and tropical integrals. And tropical integrals are quite easy to compute in practice. So all we need to do is just to give a method to compute these Berkovich-Coleman integrals, and that's it. So, I mean, I don't have time to explain the proof, but let me just say that Besser and Zerbes prove that the Vologodsky integral on the left-hand side is locally given by Coleman primitives. I mean, this is good, but it doesn't help in practice, because in practice, we don't know how to compute these primitives. We know how to compute definite Coleman integrals. So in that shape, this equality does not help. And in that end, I show that their difference is exactly the expression right here. So I reformulated their result in terms of Berkovich-Coleman integrals. And here we have this result. And as a corollary, these two integrals, Vologodsky integral and Berkovich-Coleman integral, coincide if there are no CIs. It means that if gamma is a 3. Okay, when this happens exactly when the Jacobian of X has good reduction. And in particular, if X has good reduction, because we know that if curve has good reduction, Jacobian has good reduction as well. But it might happen that curve has bad reduction, but Jacobian has good reduction. Okay, so this is the comparison formula. So finally, let me go over this example. Again, we will consider the same hyperelliptic curve. And recall that 5 is a prime of beta reduction, and this is our special fiber. And here we will consider x over q5. I mean, at 5 we have beta reduction. And my goal in this example is to compute the Vologodsky integrals of omega 0, omega 1, omega 2, omega 3. And omega I is, as usual, is defined as x to the I times dx over 2y. And R and S are these two rational points on our curve x. So let me say that omega 0 and omega 1 are holomorphic, regular one forms on x. But the other two has poles at points at infinity. So here we are not just computing integrals of holomorphic forms. So okay, in the end we will get a number, and how can we be sure that these numbers are correct? Unfortunately, there is no general rule for this, but there are some tests we can do, to check the correctness of the algorithms. So according to LMFDB, this is a certain database that contains a lot of information about curves and Jacobians, etc. The Jacobian of this curve, the Q rational points of the Jacobian of this curve is isomorphic to this torsion group here. So rank is 0. And this implies that Vologodsky integrals of omega 0 and omega 1 must vanish. I mean, this is just an important property of the Vologodsky integral, as long as we consider only holomorphic forms. And if we have two rational points whose difference represent a torsion point in the Jacobian, it must be vanished. The reason is that the Lie algebra of the Jacobian is torsion-free. So if we are right, we should see that these integrals are 0. Okay, we will apply the comparison theorem, and we need to construct a semi-stable model. Well, actually, we will construct a semi-stable covering. I am not going to define it properly, but let me say that this is an essentially equivalence notion. And surprisingly, I mean, most of the time, constructing a semi-stable covering is easier than constructing a semi-stable model. And actually, I know that there are some papers in which the authors construct semi-stable models of some complicated curves by actually computing semi-stable coverings and using the relation between two. So, I mean, this is an important step. I mean, especially for the algebraic geometry people, because we know that semi-stable models exist, but constructing them is not easy, especially for complicated curves. But this is a method. But I mean, personally, I'm just interested in integration part, so I don't know much about these objects. And the idea is for us to construct a semi-stable covering of P1 first, like we do in the classical algebraic geometry. Then we will pass to our curve. And in the first paper, the one which is joint work with Eric Katz, we gave an algorithm to do so. So as long as we construct a covering C of P1, then we will consider the following set. We will consider the inverse images of the elements in C under pi. It might happen that the inverse image is not connected, and we will consider the components. I mean, D is defined, the set of components of these inverse images. And it turns out that this D will be a semi-stable covering of X. And here, I mean, as usual, pi is the hyperelliptic double covered, which stands X comma Y to X. So basically, the idea is to construct a semi-stable covering of P1. So recall that the polynomial F is a product of two factors over Q. It's a quadratic factor times a polynomial of degree 4. But over Q5, it is a product of three quadratic factors, F1, F2, F3. And also it is true that every polynomial right here will be a square modulo 5. So, I mean, we can just assume that F1 will reduce to X squared, F2 will reduce to this expression, etc. So the set C is defined as the set containing U, U1, U2, U3 is a semi-stable covering of P1, where these spaces are defined like this. So, I mean, yeah, it is not clear to see this, but this is exactly what it is. So the algorithm basically gave this. And as you see here, we remove 3 closed disks from P1. But for example, this closed disk is contained in this open disk. So the union of all of them is give P1. I'm going to show you a picture. It will be clear more. And notice that fj is a polynomial, is a quadratic polynomial. So it has two roots. Let's call them beta j plus beta j minus. And what you can easily see that these roots belong to one and only one element of C, and namely uj. So this is the picture. So here we have u. It is just this yellow area, P1 minus 3 closed disks. And the roots lie on the boundary of the closed disks we remove from P1 to get u. And here we have u1, u2, and u3. All I'm saying is that even though it is not clear in that picture, these roots do not belong to u. They belong to u1, u2, u3, etc. So this is our semi-stable covering. Okay, then we will try to understand the inverse images of these elements under pi. So let me define this an expression Lj in terms of Aj and Bj. So what are these? We call that Fj of x is just x squared plus Aj(x) plus Bj. Right now, it is not clear what is this, but I'm going to explain it will be clear. But first of all, as you see, this is a series. And one can easily check that Lj is convergent away from D, where D is the first, second, and third closed disk I remove from P1 to get U, if J is 1, 2, and 3 respectively. So for example, U is defined as P1 minus these 3 disks. So all of these are convergent on U, for example. I mean, we will be working with this series, so we have to be sure that we have convergence. And an easy computation show that for x in the domain of convergence, the square of this expression after this computation is nothing but fj of x. So all I am doing here is that I just construct a reasonable root of our polynomial. And our spaces are so nice in the sense that the corresponding series will converge. Okay, what do I mean by that? Here we have a set. On the left-hand side, we have the inverse image of u under pi. And on the right-hand side, we have this curve. Whenever x and y is in this set, it means that y squared is equal to f of x. This expression will satisfy this equation. The reason is that, the denominator here is just a root of f of x. So by construction, this is true. And each one of them is convergent on u, so that it's a well-defined map, it is non-zero, etc. And it turns out that this is an isomorphism. Okay, on the right-hand side, as you see, y tilde square is just plus or minus 1. And so on the right-hand side, we have the disjoint union of two sets. And here I'm just saying that v plus and v minus denote the component of this inverse image corresponding to plus space and minus space. So as you see, U is connected, but it is inverse image is the disjoint union of two spaces. So this is possible. So we will play the same game for other components. I'll do this just for once. So here we have the inverse image of uj under pi, and here we have this polynomial. And because of the same reason, this map makes sense. For example, if j is 1, we will see here L1 of x. So these L1s cancel. And on the denominator, we have L2 and L3. But we call that L2 and L3. These are convergent away from the closed disk. So everything makes sense here. And again, this is an isomorphism. But in this case, the space on the right-hand side, it is irreducible. And we just set Vj to be this inverse image. So all in all, if we consider the set D, which consists V plus minus, V1, V2, V3, and this is a semi-stable covering of X. Recall that we have two fixed points, R and S. R is 1, 2, S is 1, minus 2. And these two elements respectively belong to the components v plus and v minus, and this is the picture. So we have 5 components, v plus, v minus, v1, v2, v3, and r is somewhere in v plus, but I mean, you can easily check that it doesn't lie in the intersections at all, and similarly s is here. Of course, I mean, this is not a Berkovich space, it just helps. Okay, so here are the dual graphs, gamma and t. I mean, here, as you see, v plus and v1, they intersect. It means that there is an edge between two. For example, v1 and v2, they don't intersect, and there is no edges between v1 and v2. So basically, these dots represent the components, and whenever we have an edge between two components, it means that they intersect, and vice versa. And same idea for the covering of P1. Here we have 4 components, and U and U1 intersect, etc. Okay, so we have a point here, 1 point here, and we want to compute an integral from S to R. So somehow we need to pass from S to R, and to do so, we need to choose an orientation. And I choose this orientation. I mean, the result won't depend on this, it just helps, but I just picked that one. And we need to compute the cycle space of this graph. As you see, I have 2 obvious cycles here. One of them is defined as E1, E2, E3, E4, and similarly E3, E4, E5, E6. And it turns out that these 2 are a basis for the cycle space. And an easy computation shows that the tropical forms eta 1 and eta 2 defined in these formulas are a basis for the tropical space, so that the tropical integral of eta j along Ci is going to be a Kronecker delta. Recall that that was the condition before the comparison theorem. Okay, so we have this formula. Again, on the left-hand side, there is a Vologodsky integral we want to compute, and on the right-hand side, we have a bunch of Berkovich-Coleman integrals. And here, gamma is a path in the Berkovich space from S to R, and gamma I is a loop in the Berkovich space, lifting Ci. That was the comparison theorem. So now we want to construct these paths. Basically, in order to pass between different components, we will pick reference points in each intersection, as I show in this picture. Here we have edges E1, E2, E3, E4, etc. And in every edge, we have a point, P1, P2, P3, P4, etc. And again, the results won't depend on these reference points because we just basically compute the same integrals. Okay, I am just picking my gamma as the concatenation of gamma 1, gamma 2, gamma 3, where gamma 1 is a path from S to P1 in V minus, gamma 2 is a path from P1 to P2 in V1, and gamma 3 is a path from P2 to R in V plus. I mean, it is not easy to follow in this shape, so let me give you this picture. Here we have a S, here P1, P2, and R. I'm just saying that this is gamma 1, this is gamma 2, and this is gamma 3. And as you see, the whole thing, the union of these 3 smaller paths, is just a path from S to R. So this is exactly what we want to do. And similarly, we will construct these loops. Again, this is the formal definition, but it is a bit hard to follow in this shape. So let me give you this picture. Here we have the reference points. For example, the first path, the second, the third, and the fourth. And the union, as you see, is a loop. And similarly, here we have the first one, the second one, the third one, and the fourth one. This is a loop. And as you see, the first one is thicker than the other paths. It's not because this path is more important than others. I mean, it's because I'm just a terrible painter. Sorry. This is the best I could do. Okay, these are our paths. And okay, what is the advantage of this? I mean, Berkovich-Coleman integral is additive in paths. So we have these equalities. Recall that gamma is a union of gamma 1, gamma 2, and gamma 3. And similarly for the others. On the left-hand side, there are Berkovich-Coleman integrals we want to compute. And on the right-hand side, we have smaller Berkovich-Coleman integrals. And by construction, every path on the right-hand side lies in a unique component. This is how we construct them. But recall that Berkovich-Coleman integral is local. It means that we don't have to compute the integrals on the right-hand side on the complete space. We can just compute them on the corresponding smaller spaces. For example, this gamma 1, if I remember correctly, lies in the component V minus. Okay, what is the advantage of this? Again, recall. So V plus, V minus, these are isomorphic to this space. And similarly, Vj is isomorphic to this space. I mean, Berkovich-Coleman integral is functorial. It means that if we want to compute an integral right here, using the functoriality, we can just compute them right here. Okay, we have an isomorphism. Consider the restriction of these forms to this space and consider the corresponding pullbacks. As you see on the right-hand side, there is no y, there is only x. It means that the corresponding pullback will be an expression in x times dx. So the integral of such a form is it's very easy, just calculus 1. For the other components, this is not true anymore. On the right-hand side, we have a curve in x and y, but recall that fj is a polynomial of degree 2. So this is a rational curve, and we can parameterize this curve. So again, the corresponding pullbacks will be represented, can be written in terms of a parameter. So all these cases, integrations are easy. And finally, our computations give the following list. This is the Berkovich-Coleman integral, and these are the Berkovich-Coleman periods, and these are the outcomes. Okay, by construction, the image of tau, the image of gamma under tau is just E1, E2. And if you remember, eta 1 takes value 1 over 3 at E1 and E2. So this tropical integral will be just 2 over 3. And this is again quite easy. The second tropical integral will be minus 1 over 3. So combining everything, we get these results. And as you see, as expected, the integral of omega 0 and omega 1 vanish. So these results consistent with the fact that omega 0 and omega 1 are regular, but omega 3 is not. Another thing I want to say here is that finally, as you see, integral of omega 2 is also 0. First of all, this is another contradiction, but it is unusual, and I believe that there must be a geometric reason behind this. But to be honest, I don't know why this is happening. But again, I mean, this is not a contradiction. So there must be a, I don't know, theoretical reason for this. So if you know, please let me know. Yeah, that's all what I want to say. Teşekkür ederim.
Thank you very much, Enis, for this very nice talk. Are there any questions? Okay, actually.
I was too fast.
Maybe,
again, sorry.
Maybe I ask one question,
Please.
Which is the usual one, I would say. So how about non-hyperelliptic curves? Could you tell a couple of words about it? Like if you ever taught or, yeah.
Yeah, okay. I mean, as I discussed in the algorithm, there is a step which is almost equivalent to computing a semi-stable model of our curve. And for a general curve, this is not easy. But for hyperelliptic curves, you know how to compute semi-stable models. So this is one thing. But I believe that right now, it must be possible to extend everything for super elliptic curves. These are just another class, I mean, more general class of hyperelliptic curves. So I believe that this must be quite easy. But for general curves, again, with Eric Katz, we are working on this. So the idea is a little bit different. It uses more tropical geometry. Hopefully, this will be possible. And not for arbitrary curves, but hopefully it will be possible to do this algorithm on more general planar curves using some tropical geometry again. But I mean, this is a work in progress and it will take some time. So basically, we are using the simplicity of the equations of hyperelliptic curves. This really helps.
Okay. Thank you. And the second question is that if we want to use your algorithm, how do we use it? Like looking at your paper and then try to implement, or you already have an implementation?
Yeah, unfortunately, we couldn't implement this algorithm. And the reason is the following. Basically, okay, our algorithm relies on known Coleman integration algorithms, which are all implemented, but for curves defined over QP, not over general finite extensions. But in our work, the idea was to cover my curve with spaces, each of which can be embedded into a curve of good reduction and make use the known Coleman integration algorithms. But it might happen that the corresponding curves defined over a non-trivial extension of QP, even though I start with a curve defined over QP. So because, the reason is that, whenever, we have a curve defined over QP, but the semi-stable model possibly defined over a non-trivial extension. So because of this reason, Coleman integration algorithms that we need are not complete. So it was not possible to implement our algorithm. Actually, it was not quite easy to find examples to work with, because there are so many conditions that have to satisfy. But yeah, unfortunately, this is not possible. Another thing is that, okay, if you remember these reference points that lie in intersection, they lie on highly ramified extensions, and we can define these extensions in Sage or Magma. On the other hand, time to time, we need to work with unramified extensions. These are also implemented in Sage and Magma. But whenever we try to combine these extensions or try to create a general extension, this is not implemented in the great generality. So in theory, we need this, but in practice, unfortunately, this is not possible. So one way of doing this is just to implement general algorithms for p-adic extensions in Sage or Magma, but that will be hard. That will be maybe at some point, maybe in a few years later, we will implement this algorithm. Okay,
thank you. Any other question, remark, comment? If not, let's thank Enis double time that I missed the first time.
Thank you.
Thank you very much. Now we can stop recording, Enis.
Stop recording.